but I will focus more on the how we do our science, and what is the context, what are recent developments that in computing, data science, statistics, data analysis that I personally and in the research group of Tim Schlabach, who are senior scientists, we're very excited about. So I think the most important context to be given is that currently the European Space Agency has among several missions, has the Euclid mission running. And this is an artist's rendering of Euclid. So it's literally a camera. There's some solar panels, some back end. I'm actually not an expert in the electronics. It's a camera to me. And it is a potent optical and infrared camera on board of the satellite, which I was told is at the Lagrange point 2. And every 72 minutes, 470 minutes and 2 seconds, it takes simultaneously 1 optical and 3 near-infrared photographs. Simultaneously. This is documented in the first paper from the Euclid Consortium with our posthumous PI. And this is how such an image looks. This is a photograph, and in the background you see the many chip plates of Euclid. And this is literally to scale with the image of the full moon at night. So if you were to look at the full moon at night, it has an angular extent on the sky, and the image that Euclid takes, each single exposure of Euclid, is somewhat larger than the full moon, and it looks at this patch of the sky for 70 minutes at a time, and then it moves to the next patch of the sky. One image is slightly larger than the full moon, and that makes 0.5 square degrees approximately of area. We take, because of the moving around and resetting the camera, we take 20 images per day for 5 years. We will be taking them for 5 years at least. We might extend the mission. 1 year is already in the can. Now, each such image contains individual sources that you can detect, and each such image contains 120,000 images of galaxies. So we expect, by scaling this simply, that we will get a catalog, a list, we call them catalogs, but they are lists, a list of 10 to the 9 galaxies over the 5 years of operations of this mission. And so I think this is, a very nice starting point to understand why we might, what does it mean? What is the data volume we're talking about? What rough science are we very interested in doing? This is a first image in the very first stages of the survey, which Tim Schlabach and our PhD student Henning Janssen and Kleinebrein, Tim's online item, have analyzed. And so this is one such image. Now I rendered it in colors by putting into the different RGB filters the optical and the infrared images. And we analyzed this image, which is centered around an object here, or a known object, the massive cluster of galaxies Abel 2390. And what we plot with these whiskers is the coherent distortion, the average shape of galaxies behind this object, in a pattern that schematically would be something like this. These would be the ellipticities, the shapes of the background galaxies, these very faint galaxies here in the background, and they are coherently distorted tangentially. And these whiskers are, in each of these broad pixels, their average orientation of these ellipses, and also strength of the ellipticity. Why does this pattern emerge? This is a result of general relativity. So I have here a small sketch. Consider the observer being down here, the massive object here, and this is an exaggerated representation of the plane of the sky. This is an exaggerated representation of the shape of the image. And now from the 2 edges of the galaxy, 2 light rays will travel towards us. And because gravity bends space-time, these light rays are deflected by the gravitational potential of the object. Now the light ray which is slightly further in will feel a stronger gravity and be deflected more than the light ray which is slightly further out. And so there's a differential deflection. I rendered alpha 2 slightly smaller than alpha 1. So the deflection angle alpha 2 further out is slightly smaller. Now, if you trace the optics back, the apparent redshape is squished because of this differential deflection. And this is called weak gravitational lensing effect. So you see the position of the object is offset and the shape is slightly squished, exactly tangentially as rendered in this schematic. And so this is gravitational lensing, and this is our main tool of using these 10 to the 9 galaxies. Given that this squishing, this tangential squishing, which is detected in the data with these whiskers, is due to the gravitational potential, we can reconstruct the mass distribution of this object, of the total mass of the object. And so weak gravitational lensing and Euclid will make all matter, also the invisible dark matter in this object, visible through a so-called weak lensing reconstruction. Now, in reality, the weak gravitational lensing signal leads to a 1% distortion approximately, but the average ellipticity of galaxies is 30% because they come in very different elliptical arrangements. So we need to compute an average distortion as a function of the distance between several lenses and several sources on the sky. And so we could think about schematically having several galaxy clusters and several ellipticities of our galaxies at a given separation. And what we then compute is that we average in given distance bins. So here is bins of distance. And these are, each panel is a set of galaxy clusters with typical properties. And each point is the average distortion of the background galaxies at this separation from this population of lenses. This is the correlation function between two random fields, the field of galaxy cluster positions on the sky and the field of shapes on the sky. It's a correlation function, and it has a very strong analogy to signal processing that I wanted to highlight in this general context. So when we look at these fields traced by our galaxies on the sky, we perform correlation functions among different properties of them as a function of separation between pairs to extract informations on the underlying fields and on their joint relation. So the correlation functions are great because you can easily measure them, and they provide you access to the power spectra of these fields. As in signal processing, the correlation function between of a signal in time, the time domain, is directly the Fourier transform of the power spectrum in frequency domain. For us, instead, the correlation function in spatial domain is the counterpart to the power spectrum in spatial domain. And why is the power spectrum convenient? It's the amplitude of Fourier modes. So it's exactly how you would solve a partial differential equation in space, going to Fourier space. This is why this is convenient. And so in our group, we are specializing on measuring these correlation functions. I personally am specialized with some of our PhD students present, so with none of the PhD students present, which are working on the correlation between clusters and shapes. Benjamin Chizi, I will talk about him later also, and Jaheen Shahrinar, they work more on the correlation between galaxies and shapes. So instead of using galaxy clusters, you can use the positions in real galaxies. Independent FDF fellow in our group, Dr. Laila Linke, works on the autocorrelation between shapes. Why not? No, you can also measure that. And then if you only use two-point correlation functions, you will always know something about the variance in your field as a function of scale. How do we get something about the skewness and the isotropy? Well, let's measure correlation functions with 3 points, 3-point correlation functions. So what is the average for a given set of distances 1, distance 2, and opening angles? What is the product between the shapes as a function from the galaxy cluster, from the galaxies? Or we can correlate 2 galaxy positions and 1 shape position, or again, Dr. Linke's specialty, we can correlate 3 shape positions with each other. And by looking at the 3-point correlation function, we are investigating the skewness as a function of scale, and also the skewness as a function of opening angle. to map out the properties of these fields more precisely. And so, yeah, my future PhD student, current master student, Leo Stettmann, is working specifically on this topic here. And this is the current PhD project of Jadine. And Benny is working on something akin to this. What is the takeaway point for you, besides the technicalities? The ESA mission will catalog 10 to the 9 clusters, and using tree-based algorithms, we can efficiently compute these correlation functions among the galaxy positions, also based on their galaxy properties. And this allows us to map out the matter distribution in the cosmos, because we will reconstruct the properties of the fields that the galaxies trace. And so this is the workhorse of observational cosmology. This is our bread and butter analysis tool, and I just thought would be interesting for you to know. I will come to some implications of this later. You might notice that we always have these ellipticities of galaxy shapes in all of these estimators. And so what you can think of is that the ellipticity of the galaxy, because it traces the gravitational potential through the lensing effect, is our total matter detector. It is the distortion of the galaxy shape, which tells us how much matter there was in that position, which traces the matter field. And so we need actually to calibrate our ability to measure the ellipticity of galaxies in the Euclid survey, as you would have to calibrate any detector that you use. So this is how a galaxy would look in perfect observing conditions. Infinite exposure time, no distortions, except for the pixelization of the screenshot I take. So it could be more higher resolution even more. It is now distorted by the gravitational potential, and this distortion is our signal that we need for all the galaxies. Again, here it's highly exaggerated. It is now seen through the atmosphere and through our optics of the telescope, and is therefore distorted by the optics of the telescope. It is pixelized by the detector, because we can only detect the number of photons or the flux from photons in specific pixels. And then there is this healthy amount of observational noise on top of it. And so in reality, this distortion here will have to be reconstructed from the measured ellipticity of a few suspiciously bright pixels that we managed to detect at 5 sigma. And this is how we get 10 to the 9 objects, of course. Now, there is one saving grace, is that stars are point sources, and they are not sheared because they are point sources, so there is no differential deflection of light rays. They, however, go through the same optics, same detector, and see the same noise. So some parts of this process we can hope to control by understanding the image that a star gives us. However, for the rest, we need large calibration simulations with highly realistic galaxy images inside our simulations for our calibration. And how do we go about this? This is work that we did with Benjamin Chisi. By now, I think, then we can say you are senior PhD student. We need to generate realistic galaxy images, and so we trained a generative AI framework to do this. We have noisy images coming in from precursor space missions, and we compress we can compress them with an encoder strategy to a latent space, embed desired galaxy properties in the latent space, and then train a decoder so that the input matches the output. Now, this is an autoencoder. It's nothing very, it's 10 years old technology. I think what is interesting, well, the decoder can be used to generate synthetic images from a sampling of the latent space and the embedded galaxy properties, and it uses a deep transposed convolutional network to upsample images, completely standard technique for image generation. This deep transposed neural network here allows you to have a very high fidelity, and you can train this to accurately arbitrarily good fidelity. Again, this is 10 years old technology that we used here. You could think about using diffusion models and so on. We can talk about why we didn't do that specifically. Now, what is new for us, and what I think is interesting, and what I would like to maybe discuss with some of you, is that the encoder is actually custom designed to have physically motivated convolution kernels, and not general convolution kernels. Because a general convolutional neural network can have any kernel to compress. But we know that galaxies don't take any shape. I mean, they have to be gravitationally bound objects. They cannot be completely fluffy or ridgy. They have to underlie some physics. And so in the kernels for the encoding are so-called wavelet scattering transforms, or they are also, as a physicist, I would say, these are the eigenstates of the quantum harmonic oscillator. And this is one of these typical cases one has to sit together carefully and just compare the vocabulary. What one person might call wavelet scattering transform, for the other person are the eigenstate of the quantum harmonic oscillator. And if you don't take the time to talk to people, you never learn the vocabulary translation between fields. So this is great. Why are the eigenstates of the quantum harmonic oscillator great? In my opinion, why did I suggest Benny use them for his compressor? Well, they are confined to rather natural shapes, because they have to live in the potential well of the harmonic oscillator. So they are compact, they are localized in the potential well, and they are orthogonal to each other. And by making an orthogonal compression, I know that my noise doesn't blow up non-linearly because the different kernels are orthogonal to each other. So they react linearly to the noise. And so if this encoder was designed on physically motivated kernels, we can achieve a very high fidelity also in the compression. So this is the original Hubble Space Telescope image. This is our reconstruction of that image. And you can see here the difference between the two, the residual and the noise. And you can see that we are really able to pick up also these irregular features here thanks to our encoder. Whereas typically, previously, these simulations were done with parametric models where you just fit a slightly elliptical light profile. And you can see that you're missing in the noise, you're missing all the interesting features which might impact your accuracy of your simulation. This was trained on 6,000 images from the Hubble Space Telescope, a precursor space telescope to Euclid. And so Professor Scherbak has put together this team of people where we are on track to characterize Euclid shape measurements to per mil accuracy. This is the requirement because of the large number of galaxies. And currently we are at %, but we're building up. Right? And also it's only 1 year of mission, so there's still work to do. But we have been using generative AI to create realistic images. We have been having data-driven simulations where we make sure that the simulations match the reality by using Wien copula. That's work by Henning Janssen. And we have been using high-performance computing to making these large image simulations. And all the 4 students have been working with. And all of this work is funded by the FFG mainly. So shout out to them too. Good. So we are confident we will calibrate our shape measurement detector. What is the next challenge that we have? From what I explained to you about lensing, we need to know the background galaxies, because only they are lensed. The galaxy in front of our object will not be lensed. So we need to classify these faint, slightly colored spots to find out which of the galaxies are part of the galaxy cluster and which are not part of the galaxy cluster. So what we are facing here is an unsupervised classification problem of determining which galaxies belong to the cluster and which ones are not, are average galaxies for which we have which are characteristic for the rest of the field. And here I take this colorful image from the Hubble Space Telescope Deep Field to maybe give you this one astrophysics insight. Galaxies are very nicely colorful. And now you might say, okay, thank you, I knew that. I have seen extragalactic images too. But now let's remind yourselves that the color of a galaxy correlates both with the type of galaxy. You see, spiral galaxies are more blue and elliptical galaxies are more red, but it also correlates with the distance, because the distant galaxy is redshifted. Right? And we have taken 4 images with Euclid, so we can determine the color, which in astrophysics terms is just the ratio between fluxes in different bands. So I can make a color also in the infrared by taking 2 infrared bands and make an infrared color. And so we have Euclid gives us access to the colors of galaxies in the sense that these are ratios between different bands. And we see, you can see on the left that there's a huge variety in this color and also brightness space. And how do we compress this color and brightness space? Well, we train a so-called self-organizing map on the color space. And the self-organizing map is made up of 32 times 32 neurons, which are iteratively adjusted to fill up the color space optimally and provide us a compressed representation of the color space and of the magnitude space. In the case of this precursor work in the dark energy survey, which was also a similar mission to Euclid, but from the ground, in which I am an associate member, you can see that each neuron in this cell has a specific I-band flux magnitude, a specific R minus I color, and a specific Z I color. And you can already see how the different neurons adjust themselves very nicely organize themselves very nicely into these neurons. And so the color space is organized with the self-organizing map such that neighboring pixels, neighboring neurons have similar properties. As you see, it's a gradual change in these neurons, but also you span the full color space. So the full range of colors and the full range of magnitude is spanned by this, these self-organizing map cells. And so what I am working on right now, so this is pretty fresh, but I'm confident in showing it. It's preliminary work I'm doing. I am looking at the occupation of some cells and how it varies as a function of distance from the cluster and as a function of cluster population. And so just looking at this, you will see that when we are very far from the cluster, the distribution is always the same in the color magnitude space. Whereas when we move in towards the clusters, in these four different populations, different patterns, different occupations in color magnitude space appear. And my data science challenge was to decompose this data set into the pattern in the field, the pattern in the cluster, and the relative mixing fraction between the two patterns. The method I choose to do this is variational Bayesian inference because it has the advantage of being, providing me also with a statistical error bar. And I fitted for the distribution of cluster galaxies, so the template you would see here, the distribution of field galaxies, the template out here far away from the cluster, and the relative mixing fraction. And the result of, so I had to do 4 pages of equations and a small Python script later, I was able to decompose this into these cluster fields, which look like a non-noisy shape of the pattern, of the occupation pattern here, and these field distributions, which are clearly the pattern on the other side. And specifically in the center, for each bin, the relative mixing fraction, how prevalent is this pattern and how prevalent is that pattern? Because this is a decomposition in the color magnitude space, I am now able to tell you that in this specific bin, we have 50% galaxies, which follows this pattern, and 50% which follow the average pattern of the field. And so we can actually calibrate and understand and classify the galaxies. I think this is pretty cool because this is a non-parametric decomposition of galaxy color distributions around clusters using variational inference. So it's an unsupervised classification method relying on Bayesian techniques. Good, so we know the background galaxies, we can perform our lensing measurement around our galaxy clusters. And how does this look? The catalog of galaxy clusters contain different observable properties, for instance, the redshift, the significance in the millimeter, and the number of galaxies. And we can make a 3-dimensional histogram of these properties of galaxy clusters. I have also convinced you that around galaxy clusters, we can accurately measure the tangential distortion of average galaxies, which is proportional to the mass. But crucially, in this entire setup, we do not know the mass of the individual clusters because it's very hard to determine the mass of an extragalactic object. Speaking to a statistician, we should therefore say that the masses of our clusters are latent variables in a Bayesian population model. And why is this interesting? It's interesting because the target of our inquiry is the distribution of masses. So the distribution of latent variables. Specifically, we can use the cosmological parameters and large simulations to determine which properties of dark matter and dark energy generate different mass distributions for galaxy clusters. So the task is to reconstruct the distribution of latent observables, the cluster masses, from the high-dimensional histogram of observables and from the average tangential shift. And this is the topic of which I graduated, in which I'm a specialist in. How do we do this? We do this by a Bayesian approach. And as I try to teach the master students in my course, the Bayesian approach starts with the following very counterintuitive thing for most physicists. You postulate a stochastical model with 3 parameters that is able to generate your data. This is the opposite of what, it's not you invented. You come up with an idea of how to generate the data. And then you evaluate the probability density function of the actual data as a function of the model parameters, and this is called the likelihood. How would I generate a cluster catalog if I knew the theory? I assume the cosmological model, and I assume a latent distribution of my mass of my masses. This is what the target of my inference. From this, I can draw a mass-selected cluster sample. From the distribution of labeled, I can draw a catalog of clusters with masses and redshifts, because I know the distribution is a function of mass and redshift. I then apply an astrophysics mapping where I draw for each galaxy cluster its observed properties. For instance, the SZ signal, the richness, the mass of the weak lensing. And by having a model for the physical properties of clusters. How many red galaxies are there in a cluster of a given mass? This is the type of assumption we make here. And finally, I add the instrumental noise. And this is a full generative model for a catalog of observed quantities starting from a mass-selected catalog. Sebastian Bouquet and myself, 2 years ago by now, formalized this by saying that you have to forward model your latent distribution by multiplying with all the probability distributions to generate the observed properties and marginalize over the unobserved latent variables. And this way you go from a distribution in mass to a distribution in observables. And once you have a distribution in observables, your actual catalog is an inhomogeneous Poisson process. So you simply evaluate the likelihood of observing a given catalog running over catalog I with this inhomogeneous number density of objects. And this gives us our likelihood. We can compute this. We can compute these integrals and trace their dependence on properties. How do we do this? Now, this is the place where we are a little bit archaic, maybe. We explicitly compute the likelihood of the observed population. And we model it by approximately 30 unknown parameters, 5 of which for each mapping between mass and observable, which we don't know a priori, 6 to model the mass distribution, and these 6 parameters are, among others, for instance, the density, the amount of dark matter or the properties of dark energy, and some extra nuisance parameters to marginalize over systematics. So what we do in cosmology, what is the paradigm in cosmology, is that your population analysis or your Bayesian inference resorts to an explicit sampling of a high-dimensional posterior, which you can do. You just do it. I mean, it takes a week on a supercluster, but you can do it. And here I show, for instance, the marginal contours of this high-dimensional posterior of the cosmological analysis I carried out with a team in Munich for the Rosetta cluster sample. Yeah, so this is a sample of our posterior. Now, zooming in on the interesting thing is these 2 parameters here. They are the mean matter density in the cosmos and the standard deviations of fluctuations in the matter field. And this posterior is this blue curve here. Another experiment using similar high-dimensional likelihood samplings come to different marginal contours on these 2 fundamental properties of the matter distribution in the universe, specifically its mean density and its standard deviation. This is where I don't die. So, Bayesian population modeling, high-dimensional likelihood sampling are crucial to observationally determine the structure of the cosmos. And this is another bread and butter technique in observational cosmology. I'm slightly over time, but here's my summary. Euclid's ESA mission will bring observational cosmology into an era of unprecedented amounts of data. I think this is, I showcase this to you, and I hope we can convince you also in the following years with some nice presentations with the results that we will derive from Euclid. This gives us the opportunity and the necessity, I would say, to develop AI-empowered methods to run high-fidelity simulations. And I'm just plotting here Benny's autoencoder. Here comes a question that might be interesting to discuss. Will larger training samples enable deeper architectures? Or should we still use, or are still physical constraints to our architectures? Are they still needed or desirable? I don't know. It's just a question that I have, that maybe there is other fields which are facing similar topics which might be interesting to talk about. Of course, unsupervised classification is crucial to understand extragalactic observations. Here's one example that I provided from my own work. But as a physicist, unsupervised algorithms are unsatisfactory, because I want to implement also theoretical understanding inside my unsupervised algorithm. If any one of you has managed to do that, please let me know. I'd love to. I'd love to learn. Or we can discuss how to do this, how to implement theoretical understanding in unsupervised learning. 2-point and 3-point correlation functions are the workhorse of observational cosmology. We know how to do them, we know how to compute them. Of course, there is a nagging question. Are there better summary statistics that can be tested? Is there any experience from other fields where you have to signal processing or other topics where you did not rely on 2-point and 3-point statistics to map the properties of your signal, but maybe something else that we could think about its applicability to cosmology? Finally, Bayesian population modeling and high-dimensional samplings are the current analysis paradigm in cosmology. And of course, this is an old paradigm. No? There are more effective methods of sampling, like implicit likelihood, GPU acceleration. What will be the method for the future, if not the combination of all the ones I mentioned here, or something completely new? And specifically, this topic here is my contribution to the FVF Special Research Area Dark Universe Explorations, which Tim Schrabak, myself, colleagues in Vienna won. And it started May 1st this year, so it's ongoing. And we will have a kickoff meeting at the Victor Hess building next Tuesday, where you can learn more about our interest in dark universe explorations. Our colleagues from Vienna running simulations of the cosmos will be giving the physics colloquium. So yeah, you're most welcome to join. And I conclude by saying I'm looking forward to discussing topics of joint interest and also, of course, to initiate any scientific collaborations. Thank you.